Hello and welcome. This video is a continuation of the previous one, where we talked about gradient vanishing and exploding. We will explore batch normalization. It is a third way to reduce gradient vanishing or exploding. It was introduced by Google in 2015. According to the paper, batch normalization not only reduces gradient vanishing, but also allows users to use a bigger learning rates, reducing the learning iterations. This is the overview of this video. First, let's check out internal covariant shift. When we train the deep neural network, each layer's input is the output of the previous layer. The distribution of each layer input changes during training. It slows down the training process. For some activation functions, internal covariant shift causes gradient vanishing or exploding. I will include an example later to illustrate. Next, we will dive into the batch normalization and understand how it works. It helps us to prevent the internal covariant change and reduces training steps. Then, we will use a practical example to demonstrate how to use it and its performance. Let's get started. First, let's explore internal covariant shifts. When we train a neural network like this, inside each hidden layer, first we use the input features matrix product with weights to get the linear transformation. Then we feed the transformation results to the activation function. For example, at the first layer, the linear transformation values might have a mean of 10 and a variance of 5. For the second layer, the linear transformation output values might have a mean of 100 and a variance of 20. This can be any random numbers in reality. When we use a sigmoid function as an activation function, as you can see, when the input values become larger or smaller, the derivative of the sigmoid function tends to 0. This is also called saturating of sigmoid function. During the training process, when the input values become larger or smaller due to internal covariant shifts, for some activation functions, such as sigmoid activation function, it causes vanishing gradient when backpropagation. We could reduce the gradient vanishing by using ReLU activation functions and carefully initialize methods as we discussed in the previous video. However, if we can use some methods to restrict the distribution of the linear transformation, such as restricting the linear transformation to zero mean and a standard distribution before feeding into the activation function, it can help us to achieve better results and speed up the training process. This method is called batch normalization, and it is the main idea of this paper. There are several benefits of batch normalization mentioned in the paper. First, we can use a larger learning rate without the risk of divergence. Second, batch normalization allows us to use activation functions like a sigmoid function. It prevents the network from getting stuck in a saturate mode. Let's briefly talk about how batch normalization works. When we train a neural network using a mini-batch, mean and variance of mini-batch can be calculated with these formulas. Mean is a mini-batch average of the feature x. Variance can be calculated based on the features x as well. After we calculate the mean and the variance, applying this function to each input can normalize the linear transformation. Now, the data has zero mean and a unit variance. It is ideal to feed into the activation function. There is one more step for batch normalization. We need to apply a shift and scale to calculate the final linear transformation result. So, we introduce two more parameters, beta and gamma. At this point, you might be asking if the entire process of batch normalization is to normalize the input, Why do we need to add beta and gamma? We will initial those values as 1 and 0, so that each layer will be normalized at the beginning. Then the back propagation will learn and update beta and gamma so that the output can be shifted accordingly. This result graph is mentioned in the paper. The black line is the model without any batch normalization. Bn x5 has a small learning rate compared to Bn x30. The author said after adding the batch normalization layer, the accuracy is improved dramatically. At the same time, they increase the learning rate and require less training step to achieve good results. For the pink plus line, they use the sigmoid function as an activation function instead of ReLU. And the result is pretty good as well. For any details, you can refer to the original paper. I have included a link in the description below. Now, let's move to the practical example. Adding batch normalization is extremely easy in Keras. Simply add one more layer before the activation layer. The API will do the heavy lifting part for us. I use the two sequential models with exactly the same amount of hidden layers and parameters. The only difference is the second model has a batch normalization layer. The result of the batch normalized model is pretty good. Only 5 epochs, and the end result is much better than the 10 epochs without batch normalization. As a result, the first model gives us around 85% testing accuracy. Batch normalized model gives us 87% testing accuracy. If you are training the model for the deep neural network, it is worth trying batch normalization. This is the end of this video. I hope you have better understanding of batch normalization. If you have any questions, please in the comment below and I will see you in the next video.